Today, we're talking about one of the most elegant problems in all of computer science: how to find the hidden skeleton of a network. It's called a minimum spanning tree, and you know what? It's the secret sauce behind building the most efficient networks you can possibly imagine.
All right, let's just dive right in with a classic scenario. Picture this. You're a network engineer. You've got a map with all your company's offices and all the possible ways you could connect them with fiber optic cable. Every single connection has a price tag. Your mission? Connect every single office, but for the absolute rock-bottom minimum cost. No office can be left out, but you can't afford to waste a single inch of cable. So where do you even start? This is the exact problem minimum spanning trees were born to solve. And this puzzle, finding the absolute cheapest way to connect everything without creating any wasteful redundant loops, this has a name. It's called the minimum spanning tree problem. And it's a huge foundational concept in computer science with some incredibly practical uses.
Yeah, and believe me, this isn't just about laying down some fiber optic cables. The very same logic applies practically everywhere. It's used to design electrical grids for cities, plan road networks to connect towns, and even in things like image processing to help a computer figure out where one object ends and another begins. It is a powerful, powerful tool for optimization that we all benefit from every single day without even realizing it.
Okay, so before we can find the minimum tree, we gotta back up a step. We need to understand the basic building blocks first. So, what in the world is a spanning tree? Let's break it down.
Well, everything here starts with something called a graph. You can just think of it as our map. The vertices, or nodes, are the locations, so our offices, and the edges are all the potential connections between them. But here's the key. In our problems, it's a weighted graph. That just means every edge has a weight. Think of it like a price tag representing the cost, or maybe the distance, of that specific link.
Now, a spanning tree is like the bare-bones skeleton of that graph. It's got two really important rules. First, it has to connect every single vertex. Second, it has to do that without any cycles or loops. None. This is crucial because it means there's only one single path between any 2 points. No wasted redundant connections. It's the definition of efficient.
And that brings us to the main event, the minimum spanning tree, or MST. So, for any given graph, you could draw a whole bunch of different spanning trees, but the MST is the special one. It's the one spanning tree where, if you add up the weights of all its edges, the total cost is the absolute lowest possible. It's the cheapest, most efficient skeleton for our network, period.
So, here's the million-dollar question, right? How do you actually find this one perfect, cheapest tree when a complex graph could have millions or, heck, even billions of possible spanning trees? Well, it turns out there's this one single, incredibly powerful rule that guides every single algorithm that does this.
It's called the cut property, but I prefer its other name, the light edge rule. It's just more intuitive. And honestly, this rule is the secret sauce. It's the fundamental insight that makes finding the MST not just possible, but actually surprisingly simple.
Okay, let me break this down because it's so cool. Imagine you take your map of offices and just draw a line right through it, dividing all the offices into two separate groups. Any two groups. That's a cut. The rule says if you look at all the potential cables that cross that line you just drew, the single cheapest one, the lightest edge, is guaranteed to be part of the final minimum spanning tree. It doesn't matter how you cut the graph. This rule always holds true.
And that, right there, is the magic trick. It means we can be greedy. At any point, we can just look at our options and pick the cheapest, most obvious choice right in front of us, and we can be totally confident that it's the right move for the big picture. We're guaranteed that these small, locally best decisions will, step by step, lead us to the one single, globally perfect solution. It's amazing.
Okay, so now that we're armed with this powerful light edge rule, let's look at 3 classic algorithms that actually use it to build an MST. They all have a slightly different strategy, a different way of thinking about the problem, but they all get to the exact same perfect result in the end.
First up, we have Kruskal's algorithm. Think of this one as the meticulous planner. It starts by taking every single possible edge in the whole graph and sorting them in a big list, from cheapest to most expensive. Then it just goes down the list one by one. It looks at the cheapest edge available and asks, if I add this, will it create a loop? If the answer is yes, it adds it to our tree. If yes, it throws it away and moves to the next one. It just repeats that until the tree is complete. Simple, greedy, and it works perfectly.
Next is Prim's algorithm. This one's more like an explorer. It starts by picking any random office to be its home base.
Then, at each step, it scans the horizon and finds the single cheapest connection that links its current territory to a new unexplored office. It adds that connection and that new office to its growing tree. It just keeps doing that, expanding outward, always grabbing the closest, cheapest neighbor. It's like watching a crystal grow.
And finally, there's Borufka's algorithm. It's actually the oldest of the three, and it's built for parallel processing. This one is wild. In the very first step, every single vertex, all at the same time, finds its own personal cheapest edge and connects to it. Boom! Instantly, you have a forest of tiny little trees all over your map. Then the algorithm kind of zooms out. It treats each of those little trees as a single super vertex, and then does the whole process again, connecting those super vertices. It keeps repeating this, merging forests into bigger forests until only one giant tree is left.
And looking at them side by side really highlights their different personalities. Crossgoal is edge-based. It looks at the whole world of edges at once and is great for sparse graphs where there aren't a ton of connections. Prims is vertex-based. It grows from one spot, which makes it super efficient for dense graphs with tons of connections. They use different tools under the hood to get the job done, but the goal is always the same. Now, seeing these elegant solutions is one thing, but where they really shine is in solving a huge, real-world problem that affects all of us.
So let's be clear, this isn't just some dusty old algorithm from a textbook. No, this exact logic is running silently, right now, in the background of our digital world, and it is literally keeping the internet and our local networks from completely collapsing.
I want you to meet the Spanning Tree Protocol, or STP. It's a protocol that runs inside pretty much every network switch in every office building, data center, and campus on the planet. And its entire job is to use the principles of minimum spanning trees to build a safe, loop-free map for your local network.
And why is this so critical? Well, in networking, you want redundant links for backup, right? But those extra links create loops. And in an Ethernet network, a loop is catastrophic. It causes something called a broadcast storm, a digital traffic jam from hell, where data packets get duplicated and forwarded in an infinite loop until the entire network grinds to a halt. STP prevents this disaster by intelligently finding all the loops and blocking the redundant links, leaving just one perfect active path, a spanning tree. But the beautiful part is, if an active link ever fails, STP instantly unblocks one of the backup links to take its place.
And the protocol has gotten way, way better over time. The original version, well, it was a little slow on the uptake. It could take 30 to 50 seconds to recover from a failure, which is an eternity in network time. But the modern version, Rapid Spanning Tree Protocol, is lightning fast. It can detect a failure and switch to a backup path in under 6 seconds. This is the logic that keeps our modern networks both stable and incredibly resilient.
So, we end on this really fascinating thought. This whole elegant system, from city planning to keeping the internet alive, it all relies on one simple idea, that a greedy choice can be the perfect choice. The fact that just picking the best immediate option over and over again can lead to the absolute best overall result, well, that's a pretty powerful and optimistic principle. It really makes you wonder, doesn't it? Where else in life might the best local decision lead to a perfect global outcome?